Hi, my name is Megan Liu, and in this video I will be explaining homework number 1. The first step that I took to complete homework number 1 was to perform a force analysis on the entire system. I found that in the x direction there was a force acting that was equal to negative 200 pounds. There was also a force acting in the y direction that was equal to negative 300 pounds. There was no force acting in the z direction. There was a moment about the x-axis that was equal to negative 1,200 pounds times inches. There was also a moment about the y-axis that was equal to 800 pounds times inches. And there was a moment about the z-axis that was equal to negative 1950 pounds times inches. The next step was to determine the modes of loading at point A. After observing point A, I found that the types of loading present were axial tension from f of x, torsional force from the moment about the x-axis, a bending about the y-axis from the moment about the y-axis, and a bending about the z-axis from the moment about the z-axis. Then it was time to determine the modes of loading at each individual element. First, looking at element E, there's a transverse shear force due to f of y, there is an axial loading force due to f of x, and there's a torsion force due to the moment about the x-axis. There's also a bending force experienced at element E due to the moment about the y-axis. Next, looking at the forces acting at element F, there's a transverse shear force due to f of y, there's an axial loading due to f of x, and there's a torsional force due to the moment about the x-axis. There's also a bending due to the moment about the y-axis. Now it's time to calculate the stress components acting at element E. The first stress component that we calculated was the bending force, and we calculated the bending force using equations 1 and 2. The bending force was found to be equal to negative 47.1 kSi. Next, we calculated the torsional force using equations 3 and 4. The torsional force was found to be equal to 14.5 kSi. Lastly, we calculated the axial force using equation 5, which was found to be negative 0.453 kSi. As you can see from the diagram on the side of the slide, element E experiences a normal force acting in the x direction and a shear force in the xz plane. This normal force is equal to the sum of the bending force and the axial force that we just calculated, which is equal to negative 47.5 kSi. The shear force acting in the xz plane is equal to 14.5 kSi, and this is solely due to the torsional force. Next, we have to calculate the stress components at element F. The first stress component that we calculated is the bending force, and we calculated the bending force using equations 1 and 2. The bending force was found to be equal to negative 19.3 kSi. Next, we calculated the torsional force using equations 3 and 4. The torsional force is equal to negative 14.5 kSi. Next, we calculated the axial force using equation 5. This force was found to be equal to 0.453 kSi. Finally, we calculated the transverse shear force using equation 6. This was found to be equal to 0.905 kSi. As you can see on the diagram on the side of the slide, element F is experiencing a normal force in the x direction and a shear force in the xy plane. This normal force is equal to the sum of the bending force and the axial force that we calculated before, which is negative 18.8 kSi. This time, the shear force acting in the xy plane is equal to the sum of the torsional force and the transverse shear force that we calculated before, and this sum is equal to negative 13.6 kSi. The final step is to draw a Morse circle for each individual element and to find the principal stresses acting at each individual element. First, we will look at element E. To draw a Morse circle for element E, we first have to find the center. We find the center using equation 1. Next, we have to find the maximum shear stress that is acting at element E, which is equal to the radius of Morse circle. This can be found using equation 2. Next, we find the principal stresses 1 and 2 acting at element E. We do this using equations 3 and 4. And finally, find the angle, phi of p, which is the angle at which the principal stresses are acting. Using these variables that we just calculated, we can draw the individual element E and the angle at which the principal stresses are acting. And we can also draw the Mohr's circle using the variables that we just found, as you can see on the slide. Lastly, we draw a Mohr's circle for element F and the principal stresses acting at element F. To do this, we follow the same steps that we did on the previous slide. First, we find the center of Mohr's circle using equation 1. Then we find the maximum shear stress acting at element F using equation 2. Next, we find the principal stresses acting at element F using equations 3 and 4. And finally, we find the angle at which the principal stresses are acting using equations 5 through 7. After we calculate all of these variables, we are able to draw the individual stress element, F, and the principal stresses and the angle at which they are acting. And we are also able to draw Mohr's circle for element F. And as you can see on the slide, this is how you would draw Mohr's circle and the individual stress element. Thank you for watching.